So, something I assume you've never seen before. This is what I refer to as my definition of a Laplace transform. So the Laplace transform of the function f in t is defined to be the evaluation of this improper integral. Now, I'm not going to tell you yet how to use a Laplace transform, but in the future, we're going to use Laplace transforms to solve what we call differential equations. This semester, that will not happen, but this semester we'll at least get an idea of what a differential equation is and maybe even discuss some techniques for solving them. But this semester, we're not going to use Laplace transforms to solve differential equations. I'll say that for a couple more semesters. For now, we're just here to be able to construct a Laplace transform merely because it's an example of evaluating an improper integral. So this is my definition of a Laplace transform. Now let's put it to practice. So let's find the Laplace transform of this function right here, e to the at, where a is just a constant. By definition, the Laplace of this f of t is this improper integral I don't, in my usual fashion, do you mind if I exploit the fact that I have limited board space? So allow me to take a couple steps at one time. Because I've got an improper integral, I think I can rewrite that as a limit of a proper integral. And if you don't mind simultaneously combining those two factors in the integrand's position. Of course, to anti-differentiate this, again, our deep, deep REM sleep is an absolute piece of cake. So I've anti-differentiated. Now I will evaluate from lower to upper bound of integration. Oh, everyone, it looks like I did pretty much fail with my board space. How about just flipping it? Shoot, now my short-term memory is coming in. So I evaluate the antiderivative at the upper bound and lower bound of integration. Of course, I do think I'm left with e to the 0 power period in the second term, but that's simply going to be a positive one after the subtraction symbol. Now, as far as the limit of the first term is concerned, I actually don't know what's happening. I guess it all depends on what s is. Think about it. If s is bigger than a, then I think this is a positive coefficient. That makes this a negative coefficient up front. And so I've got a negative constant times x. I think as x increases that bound, that thing's going to go to 0. However, if s is not strictly larger than a, then I think this right here is going to be negative or equal to 0. Let's consider it being negative. That makes it positive. That means this thing is going to increase that bound. That being said, I do think I'm left with negative 1 over s minus a times, if this thing goes to 0, I'm left with a negative 1. But that thing's only going to go to 0 if s is strictly bigger than a. That being the case, I guess what I just found is following. That the Laplace transform of this exponential beast right here is nothing more than 1 over s minus a, given that s is strictly bigger than a. Jeepers, that wasn't very challenging, was it? So maybe I'll slip in a bit of challenge to my next Laplace transform.